the higher order surface representation and first order abstract syntax tree and the type de Broglie notation, which allows us to basically maintain the type during compilation. And today I'm going to talk about the kind of two main optimizations we do on the AST, which really are critical to achieve good performance. And I talk a little bit about the LLVM backend. So I said yesterday, like we went through all that work with the de Broglie notation and threading all the type information through the environment, through the variables. And then I said, well, unfortunately, there's still one big problem with this representation. And consider this kind of expression. It's a bit of an artificial kind of computation. I annotated the types just for clarity. And try to think about what the abstract syntax tree for this expression would roughly look like in Accelerate. So judging from what we know so far. So we have this function, define this function +1 here. We use it here to calculate 3, and then use 3 here twice, and then in here we reuse the +1 function, and we use 9 a couple of times. So for the abstract syntax tree, kind of conceptually, that's what it looks like. So here's the +1 function, and it's basically been reused all over the place. So that's the expression which represents 3. And, so the symbol basically represents an application node. So this means function plus applied to 1, applied to 2. Okay, so we have lots of basically expressions which are used multiple times. And that is what conceptually the abstract syntax tree looks like. But if we would be able to look at the actual data structure which GHC or the Haskell program creates at runtime, and that's not different like from Haskell to any other reasonably implemented functional language, it would look differently, right? No sane compiler would do it like this. So what it actually would look like, because internally it's kind of the same sub-expressions are represented using sharing, because we can do that safely in a functional language because we know that they are now destructive update. So in fact, that's what the abstract syntax tree looks like. Now, what happens if we traverse this tree? Like in Haskell, we apply anything, for example, code generation. If we apply an operation to this tree, what would happen? It basically, like if we just map the identity function over the tree, what we would get, because then it's not guaranteed that everything, that the shared expressions actually evaluate to the same thing, right? So the compiler would basically, or the runtime system would create this tree with lots of repetitions. In particular, if we just kind of apply a code generation or an evaluator or anything to it, well, the data structure becomes, for one thing, much larger, but also the code we are generating is horribly inefficient. So we have this problem that at some point in time we have this reasonable, efficient data structure, and we would actually like to generate code that mirrors this, the sharing information. But the problem is that is really just an implementation detail. Language, I can't actually observe. If I have an AST, I can't really figure out that easily where nouns are shared and where they aren't shared. So our problem is that sharing in the host language's internal representation is not readily observable, but we really need to, if we want to have any chance of generating efficient code, we really need to figure out where the sharing is. So we have to recover the sharing information. And as soon as we touch the tree, we've lost it. Like, we can't process, and in particular, we can't take the higher order AST and convert it to the Breuer notation representation straight away, because if we would do that straight away, then we would lose the sharing information, and we would get this huge data structure. So, as I said, large ASTs and expressions are evaluated multiple times. So this is really, really inefficient. And just to give you an idea about basically what the impact is, so one benchmark people really like to use in data parallel programming, data array program, is the Black-Scholes option pricing. And if we implement accelerate without the sharing recovery, so do the naive code generation, it's 20 times slower than a handwritten CUDA implementation for the GPU. And now, so just, that's the accelerate code for Black-Scholes. It's like not, you don't have to read it or understand it, just to give you an idea. It's a fairly small program. It's kind of nice to write. But if it's a factor of 20 times slower, even if it's a lot easier to write it in accelerate, it's basically a deal breaker. 20 times slower, no matter how convenient it is to write. Why, you know, then just write it sequentially. So we really, really have to address this problem. So one thing would be, okay, well, then maybe one design mistake we made was not to have a let in the surface language. Right? If we had a let construct in the surface language, then the programmer could actually express the sharing explicitly with the let. The problem about this, if you think about it, how this would actually work, because then we can't really use the host language let bindings, so it's really awkward. You can kind of thread it through in some kind of monadic notation, but it's not pretty. So that's not a good solution. So the general approach we followed with Accelerate so far was, whenever we had a problem, we tried to have a user-friendly surface representation and then do something clever during the transformation and introduce awkward, inconvenient expression internally. So the question is, can we have let in the internal representation kind of convert it without losing sharing? And the problem, like for that, we have to be able to observe the sharing in the AST graph. So we have to observe the implementation detail pure functional languages abstract about. So for lots of other languages, it's actually possible to have equality, referential equality. So if I have two objects and I want to compare them, and in our languages, that's often the default for comparing two objects. It compares whether the pointers, the references to these objects are the same. Any idea why that's not the case in a pure function? Pure functional languages offer that.
Maybe in pure, because then the equality depending on the internal representation of the runtime.
Exactly, and it also it's impure, and it can actually change because garbage collection, right? If an object is garbage collected, it'll be somewhere else. Again, it's made even worse in some sense in a lazy language because look at, like, if you have something, let z equal first of x, y equal second of x, and then you try and figure out whether z and y are the same. They are the same, and like x is some object. So they are the same. They should kind of point to the same x, right? But is that true in a lazy language? In a lazy language, what's z and what's y? It's a closure basically, which unless it's evaluated. So if you look at it while it's unevaluated, z and y would be different, like different referential. And then you evaluate it, and then they're suddenly the same. So it's definitely a side effect. So we can't really, it would break a lot of stuff. It would break garbage collection, a lot of compiler optimizations really rely on critically in a functional language. Luckily for us, basically, referential equality, basically something like that, is not only needed for the implementation of embedded domain-specific languages, and this is really a problem not only Accelerate has. Every embedded domain-specific language which cares about the performance will have to deal with sharing recovery. So luckily, other people have basically that problem as well. So for example, if you want to implement normalization, or it's also really useful for constant comparison of large data structures, when you say, well, I don't necessarily care that I always get I might get false negatives, but most of the time I want to compare big structures really quickly without having to traverse the problem. And Eagle was, for their hardware description language, Lava was basically, I think, the first person who used what's called stable names, so the point is it has to solve this problem. So there's this Haskell library which provides an abstract data type called stable name, and if I have an object of any type A, then make stable name returns just a name, and the guarantee with this name is that this identifies the object and is not affected by garbage collection or anything. So this means, for people not familiar with Haskell, this means that it's a side effect. So if you kind of expand this type, it's a type which takes a world and returns a stable name A and a new world conceptually. So it's still basically kind of a pure function in that sense, because it makes it clear that the world, it means the world and the world is accepted. Then we have hash stable name, which given a stable name returns an integer. It doesn't necessarily have to be unique. In practice, it often is, so it's a very good hash key if we want to maintain a hash table where we look up the names. And then we have we can compare stable names for equality and order. So there are some guarantees, basically, the stable name. So if I have, if I get the same stable name for two objects, then I know these objects are the same. So there are no false positives here. But and then kind of make stable names obviously doesn't return the same name, so that's basically just flipping the same statement. But also concrete, if x and y are the same, there's no guarantee that I will get the same stable names for it. In practice, I kind of do, but the library doesn't give me guarantees. So it's kind of constant. So the idea is then, well, now what we can do is basically take this data structure and traverse it, and before we visit the children of the data structure, we get a stable name for each node, and then we keep track of that. So just to give you a bit of a more concrete example, like here I have just a kind of very small version of an expression language, and here this expression is kind of similar to the expression in our example. And I have a traverse function. So it takes an expression A, and what it does, it basically just kind of, so we can observe it, it collects, it makes a stable name for each node. It collects the stable names in a list and removes all the duplicates. So for constant value, I make the stable name, and then I convert that into an integer value and return it as a list. For the multiplication and addition, I make the stable name for the parent node, or for the node, and then traverse both subtrees, and then put all the hash keys in one list, and now just removes all duplicates. Does that make sense so far? So, and here, I said, well, now let's first traverse the expression sharing, and then I touch share. I call this function touch sharing, and touch just kind of traverses. It's the identity. It doesn't do anything with the tree. It just kind of walks down the tree and returns the same result. And if we run this program, here I basically first I print the nodes I get when traversing it, when traversing the original thing. So I get really just the nodes which, the number of nodes which were in our shared AST. It's a few less because this one doesn't have explicit application nodes. So addition is really just one node. And then if I apply this kind of identical kind of traversal on it, then the tree is expanded. So the algorithm then is actually pretty straightforward. How I have this abstract syntax tree, and I use stable names to annotate each node with a stable name. I just chose here just integers, right? So 1, 2, so I go to kind of the first 3, 4, 5, 6, 7, and then 8, 10, 11. And now here I would actually touch a node, and I will get a stable name which I already have. So I keep track. I can kind of create a hash table or something where I, depending on, keep track of the stable names I already have. And as soon as I encounter a node for which I get a stable name which I already have in my list, in my table, what I do, I kind of points to a basically stable. And then I continue and kind of create a tree where the shared nodes are represented explicitly. And now, because I want to kind of now add left expressions, so what I have to do is for each of the shared nodes, I have to basically float it up the tree to find the first dominating edge so that it's defined before it's used the first time. So here, for this tree, basically I have to plot it all the way up because it's directly used before this, this edge. And then I insert a left binding for this in my abstract syntax tree and replace all the references to this shared node with the variable in the left line. And I use kind of regular variables, not deploying indices here because it's useful. Then we do the same thing for node number 8 and float it up here. And then the next tree is this one, and it's just used in this subtree, so it flows up to here. And now we've kind of recovered a tree where the sharing, where we introduced the sharing that was before that in the host language. And now what we do is basically we fuse the two transformations, the De Broglie conversion we talked about yesterday, and the sharing recovery in one. Because we can't do the De Broglie first, because otherwise we would destroy the sharing information. But it's a lot easier to kind of do the at the same time. There's one less nice property about this transformation. I don't know if you had time, so I didn't have time, sorry, yesterday to put up the code, which to send the code you see now, which I promised you I will do that today. But I don't know if you have time to think a little bit about how you actually could convert a higher order representation into De Broglie. So the way you can do that is kind of track for the variables, replace the variables with their binding level, and then express that De Broglie, as a De Broglie index. The problem with that is that you lose temporarily basically the type information. And the way we deal with it is that we have, for this one step, a dynamic check. We reinsert the type, but we briefly kind of lose some type information. I don't have a proof that there isn't a way to do that completely type safe, but one good indication that this might at least be a real problem. At the same time we were basically working on this, wrote a paper published in the Haskell Symposium just about unembedding basically embedded languages. And so the De Broglie conversion they describe in that paper is essentially similar to what we do here, but they don't deal with sharing. And they came across exactly the same problem, and they said, well, it's kind of unavoidable to lose the type information. So there's this bit of not quite so nice. But we start with the typed syn AST, and after the transformation we have a type. Just quickly about the side effects. So we run, the transformation needs this side effect. It's an IR computation. But we run it inside unsigned perform IR. So basically, you can't see the outside, but we internally use the side effects. That is
okay because basically the side effect we have is something that doesn't affect the results on the outer level in any way. Like even if, even if you couldn't recover the sharing at all, it would have a different runtime behavior, but it would return the same result. So just to give you an idea about what the impact of the sharing recovery was, as I said, like initially accelerated without sharing for Black Charles was about 20 times slower than CUDA, and then with sharing, we're actually slightly faster than the hand-written CUDA implementation. And that's for one single reason. We do one common sub-expression elimination of one simple multiplication. And that's why this is slightly faster. So it's really important for this. So Black Charles is not typical. In general, I'll show you later on some more benchmarks to give you an impression of how much it makes on average, but it really depends a lot on the application. But you can't afford not to have sharing recovery because there are enough applications for which it's a deal breaker. So for canny edge detection, so that's the thing where you take a picture basically and you find the edges in the picture, the outlines. Here, accelerate without sharing, it's about 5% faster, no, slower than accelerate with sharing. And the reference implementation of CD, which is kind of a graphics, optimized graphics library. So we are slower than that. So these are also old benchmarks. And we addressed a couple of issues in the meantime, but we still would be slower than OpenCV because they exploit some properties of the GPU architecture which we can't. But it's kind of it's like it's in the same. It's 50% slower, accelerate, but writing it in accelerate is a lot faster. So it's same kind of roughly the same order. Fluid flow simulation, again, you see basically about a 5% speed up using sharing. So that is fairly typical for an application that doesn't use sharing excessively. But there are some where we use so that is one of the optimizations we found.
Do you mind commenting on why certain applications the sharing made such a difference versus the others? Like, is there any?
Basically, it depends, on your algorithm. If there, for example, if there are functions, like in my artificial example, which are used all over the place, and you don't have sharing, then it's a lot more lot more expensive. Or if they're just if the same computation, the same value you compute at accelerate program runtime is used at multiple places, then you basically pay for it every single time. So if you have a fairly straightforward application where everything is used only once, sharing won't give you anything, sharing recovery. Does this make sense?
Can you go back to the previous slide?
Sorry?
Can you go back to the
Yeah.
why is sharing, for the last example, why is sharing slower?
Oh, that's a good question. I'm not sure if I made a... That's a good question. I would answer it on Slack. I'm not sure if I made a mistake copying it, but otherwise I'll let you know. Thanks for picking that. So that is, as I said, the one optimization we really need. The second one is fusion. So do you know kind of fusion, deforestation? So basically a well-known problem. Any kind of collection-oriented language, parallel or sequential. So if you express a computation like here where we first map G over XS and then map F, especially in script language where we create the whole data structure in the immediate data structure, this basically means we have two traversals, and if you create the intermediate data structure, then you also need a lot more memory. And memory access is usually, unless G and F are really, really expensive functions, the cost for the memory access are actually the dominating factor. So this is twice as slow as map of F composed with G for many function energies. Because really the amount of work we do on every element is often fairly minor compared to the memory access. Then if you have something like this where you create a big data structure and then you reduce it, if you would kind of fuse that together into, well, you wouldn't even need to create a structure at all, right? You just need an accumulator, it's just a scalar operation. So if you have something like this, the non-fused operation could easily run out of memory, whereas the fused operation is no problem. Fusion in general can be really hard, but it's basically not computable to decide the optimal fusion strategy. Because let's say you have a value which is used twice and in two computations, and then quite often it's worthwhile kind of inlining it and fusing it to kind of calculate this value twice, because as I said, memory access is often the dominating factor. But in general, kind of you can't really duplicate a computation and hope that fusion will kind of amortize it, because it can kill the word complexity, like you can actually increase the word complexity. And to decide that statically for all, figure out the word complexity for all kinds of computations is not computable. So it is a difficult problem, and in general we're kind of fairly defensive. If we have a value that's used more than once, we don't fuse it. We actually create it and then use it a few times. So like sharing recovery, if we don't have fusion, then again, deal breaker. So in this case, the wonderful application is pathological case. If we don't have fusion, then it's about 10 times slower than the fused. So, and you know, that's not the typical thing, but it's on average again about 50% faster to have fusion. So you really need that. The problem is a little bit like some of the classical fusion techniques, which are used, for example, in GHC, we can't use. So one thing is the so-called default optimization. There are a whole family of fusion techniques that are kind of similar, where the idea is that traversals are expressed in these kinds of combinators, and so build is a higher order function that builds a data structure. The fold R is our linear fold R, which reduces it. And then we have this rule that if you have a build followed by a fold, you can kind of get rid of that, and it's just the application of the build function to the fold function and the neutrality. And then you can express map, for example, in terms of fold and build, and so on. So one problem with this style of fusion is it completely destroys the parallel pattern, right? It expresses it all in kind of a recursive traversal. And we can't do that because we need to maintain the parallel structure. The other problems I mentioned already, that if you do with fusion, it often relies on inlining. We want to be conservative about that. Then the other problem we have with accelerate is that fusion happens, it's a transformation of the ASD, so it doesn't happen at the Haskell GHC compile time, but at the runtime of our program. So we have to be a bit careful. It can't be something that requires too fancy processes. So on the other hand, because it happens at runtime, we also have a the other issue is basically that the way we generate code in the back end is that we have templates, like we have some things like generalized maps and generation. There's LLVM or CUDA templates where we plug in the specialized functions. So whatever our fusion representation is, has to be compatible with this template. So what we do is we kind of distinguish between two different types of functions. One, producer, which means functions where each element of the result depends on at most one element of the input array. So examples for that are map, vector mute, generate functions, and consumers, which are actually not, like the naming here is not great, because consumers can also produce new arrays. So we saw that like fold is a consumer, but the shape polymorphic fold actually returns a new array of a different shape, but it returns a new array. So examples for that are fold scans, and then stencil operations, where we have to look at, basically if we have an input array, we always look at a whole set of elements of the input array. So we treat them separately in two separate phases of the compilation. Producer are used by a program transformation, and producer-consumer during code generation. So when we generate these LLVM or these code templates, we with the producer-consumer fusion, we just kind of use it in that moment and kind of plug in the fusion operations there. We don't have consumer fusion. So if we have two folds in combination, then it still would often, there's lots of cases where it would be good to fuse that together. We don't handle that at the moment. So just an example of the effect fusion has. So let's say this is a program, so we have producers here, and the green fields are consumers. So one producer produces two arrays, one consumed by a consumer, and then the result pass into the producer. Here we have something might be kind of zip width, which takes two input data structures and consumed by a consumer, and so on. So the first stage kind of fuses all the producers. It doesn't fuse P1 in, because to do that, we would have to duplicate it. And as I said, it doesn't necessarily mean, it could be a very reasonable optimization, but we don't do that at the moment. And we have to do. Then the next step is that we fuse the consumers in. So here, we can actually only do that at this point, because here, well, if it would fuse it in, it couldn't be fed to this computation. And the way we do this is basically, it's kind of a trick that's been around since the 70s. So for producer after fusion, our arrays are not represented per default as manifest arrays. But what we represent them as are so-called kind of delayed arrays. So we remember what the shape of this array should be. And we remember how, given that shape, we can compute the array if someone actually needs it. So there are three. So a delayed array can be, array computation can either be actually something which is just a manifest. So for example, you just pass that array, the manifest array in, then it would be represented with this thing. Or if it's a real delayed array, then we just remember the shape, we remember the function from shape to expression, and then we can compute it if we need to. So basically, this kind of remembers the arguments to the generator function. And we can do that from there. And then we have, so this is not strictly speaking necessary because it's a special case of yield. So in yield, it is not actually clear or obvious in the function from shape to e. That could be a function that reads from an existing array, maps some operation to it, and then returns the result. Or it could be a function which just kind of creates it just from the shape and doesn't ever look at an existing array. So for example, if you create a function, an array with just the elements, everything has an element 10, right? So you don't need an input array to create that. That would be represented with yield. But if your function, like a map function, here we make it basically clear that we have, so this represents the argument array, and these are functions on the argument shape and the argument array. And to know this, it's just kind of useful to kind of specialize those. And as I said, this idea of kind of keeping this the delayed representation around is really old. And then the implementation of the delayed map is, so it gets a delayed array, and then it just, if the delayed array has shape, basically a step implementation, that should be, sorry, there should be spaces here. I don't know what I did. Anyway, if it has the important thing you can see here, if it has a step computation, then it takes the actual kind of computation and replaces it with the map F with G. If same for yield, and if it would be a done already, then it would become a step function. So that happens at and sometimes it's actually also more efficient, even if you can use it, and even if that doesn't mean you have to copy something. For example, often if you have a function like transpose and then a map, because of locality, it's actually faster to calculate the transpose of an array and then do the map. We don't try to make these decisions automatically. They depend on the architecture, they depend on so many things. So what we provide the user with is with a compute function, which on the surface language doesn't seem to do anything, but basically what it does is it forces an array, a delayed array, into a manifest array. And sometimes, like, you just need to try it and see where it is. So we don't have anything where you can force fusion, but we have this operation that prevents fusion, deterministically. So yeah, as I said, this is done producer-consumer, it's done during count generation, and we don't have support. And then finally, we're basically at the point where we can do the real kind of code generation. So the latest version we're generating code for LLVM. And the nice thing about LLVM intermediate representation is that it's typed. But the types are represented as a value level data structure. And what we do is we kind of track them into our LLVM file. And guarantee in this way that we only generate type correct programs. We don't, like we generated plenty of incorrect programs, but at least they were type correct. So we have a GADT to define basically to model the LLVM instruction set. So we have here this num type is one of these dictionaries, because this is kind of overloaded. So this is the explicit dictionary argument, then the operands and the instruction, and we track this just as we did it with the expressions. So the LLVM backend framework, it's basically LLVM is a reusable framework, and we tried with our LLVM backend framework to keep the components as reusable and specialize only as late in the framework structure as possible, so that a large part of that framework is reusable for future other backends. And I mentioned that a few times before, so we have two backends at the moment, apart from the interpreter. One is the vectorized multi-core GPU, CPU, and the GPU backend. And because at a later stage, for GPU code is quite different from the CPU, multi-core CPU code. Like for multi-core CPUs, we have to chop up the arrays and kind of schedule them to different courses. And just to give you kind of an idea, a bit of an overview how the effect of all these optimizations are and how it performs. So there are some benchmarks. They are not the current. So it was called the canny edge detection, right, where the sharing was slower. Yeah, so here that's without sharing and with sharing. So yeah, it must have been a typo. I think I must have switched the two, because here it's also, right?
It was the fluid flow.
Yeah. It was the fluid flow. Let me see. It was with the fluid flow. But it's the same. It's the same. The share. Yeah. So just kind of. So here the different reference implementations. Like shows we have CUDA. Can you actually take an OpenCV? And you can see here, like with the embodied implementation, without Fusion, you can't even run it, because we generate so many intermediate data structures that it just runs out of memory. But you can see even with the fully optimized accelerate implementation, it's still, so that was the only, was used to be kind of 10 times slower than a handwritten CUDA implementation. We have fixed a lot of problems it had, and so, but it's still about 4 times slower. So embody is not the best kind of implementation for us. But it's still kind of, it's in the same magnitude. Then that's sparse matrix vector multiplication for one particular application, because for sparse matrix vector multiplication, it depends, the performance depends a lot on the actual characteristics of the sparse matrix. So here is a whole, that's all for different shaped, different distributed sparse matrices. So here it's gigaflops per second, so here the higher number is actually better. And here you have the kind of optimized cusp implementation. In general, we can kind of come pretty close to cusp performance. Sometimes we are significantly slower, like here with the PEM chip, we're twice as slow. And to some extent, like even though Accelerate is a domain-specific language, for some applications it's actually not domain-specific enough. Like there are some really fast, like FFT algorithms. You really can't beat, or you would have to put a lot of work into beat that in such a language like Accelerate. And seriously, why do you want to? Why not reuse the work of other people? You know, if someone put all the work in to have a highly specialized implementation, then let's use that. So Accelerate has a foreign function interface. So this is really, if you have like some kind of matrix operations like inversion or so, or sorting, something like that, where you have a highly specialized library, then use that. You can use it in the Accelerate program using the FFI. But in general, I don't think, you know, we will have a relatively general purpose language like Accelerate will be able to beat something that is kind of optimized to the last. So just to finish up, actually, no, I was probably a bit too fast because I tried to make up the time we lost at the beginning. So Accelerate, as I said, is an open source project, and the current project members, so Trevor basically did most of the work, or Trevor from Everest on the LLVM backend. He's one of the main developers and also kind of maintainers. Then Josh Meredith is a student who is working on improving the stencil support, and Manuel Chakravarti is also still active in the project, but not so much. Like really, Trevor and Rob are the people who are doing the heavy lifting. So when I was saying like we do this, we do that, it's basically it's Trevor and Rob. So if you are looking for a project, you can kind of, if you're bored, you want to contribute to something, you're interested in computing, have a look at Accelerate. Or if you're just kind of interested in implementing something. And I hope that some of the techniques I showed you, like they are often not really specific to parallel languages. A lot of them are kind of generally applicable to domain-specific languages. So I hope you found that a little bit useful. And yeah, thanks a lot for your time.
We have the slide with the GHC for LLVM instructions.
GHC?
GHC, the data type that represents the LLVM instructions.
The one, no? This one?
No. So how large a subset of LLVM do you need?
That's a good question because LLVM change gets more and more complicated.
Do you need, for example, labels? Labels, blocks of code?
We have labels, we have blocks of code, but I would have to check exactly how large of a subset because we use the vector instructions and all of that. And as I said, like I actually haven't implemented the LLVM backend myself. And yeah, so I don't know how much we need LLVM.
And for a related question, when you specialize to a specific backend like annotate, do you give, annotate the LLVM code with specific information for that backend, or do you just let LLVM?
Yeah, we generate different codes. So different backends. But we try to push basically the point where we split as far back down as possible to make the whole framework as reusable as possible.
But you make decisions about the kind of chunking or so on. But
Yeah. We need to make these decisions, otherwise